welcome you to this morning's program. Let's discuss geothermal for heating and cooling. It is great to see such a good-sized crowd here today, and we have 24 districts represented in this room today. So we know that there is a huge amount of interest, and some of the projects that are going forward will be utilizing this technology. You all can serve as resources for one another today. Fellow superintendents, business officials, and facility staff, as well as school building committee representatives. You are the freshman class, so to speak. So as you interact today, get names and numbers, and because issues that you have, somebody else might have already dealt with that and be able to help you out. While the MSBA prides itself on trying our best to assist you along the way, sometimes you can benefit from knowing how another school district was able to handle a specific matter. And while each of you is in the early stages of thinking about the needs and wants of your new school, no doubt you have heard from community members in our community groups vocalizing interest in building a sustainable building. That is, an all-electric school, not one powered by fossil fuels. We are witnessing a rapid transformation in design of new school buildings in Massachusetts to include sustainable technology, and more school districts are including geothermal well systems in new school designs. A geothermal well system is one of a couple of HVAC options available when considering an all-electric building. The upfront cost of geothermal is sustainably greater than a conventional boiler system to heat a building. But generous state and federal financial incentives are currently available to school districts to assist with additional costs. All is it to say the availabilities of these incentives makes building an all-electric school an important consideration. A discussion of cost-saving incentives is on the agenda for later this morning, with examples of actually amounts that this school, Pine Hill, and others have applied for and expect to receive. Yesterday I was at an investor conference that the Treasurer's Office put in. I had a conversation with Governor Healy, and we were talking about what the path forward is going to look like after the election in regards to incentives and the availability of federal dollars. While that might be unknown, we know that the districts that have applied and received money is happening every single day. So that's why we encourage you to still, as your path forward, to remember that, at the end of the day, what is going to be the best for your school district as well as the environment. In preparation of the program today, we ask our panel members this question: what do you know about geothermal systems and what you wish you had known before you started? We hope that the insights of our panel members this morning will assist in guiding your team to make the HVAC decisions that is right for your project. Our objective is for you to be better prepared at the end of the program than you were when you walked into the room. Thanks again so much for taking the time to attend. We know everybody has busy schedules, but Barbara Hansberry and the team at MSBA who put these programs together is really, we find, to be beneficial. And now I'd like to introduce the superintendent for some remarks. Thanks, Doug.
Thank you very much, and I'd like to welcome you all to Pine Hill School. My name is Tim Pavovar. I'm the superintendent here in Westwood. And I will say there's a reason why I am giving the opening remarks and not sitting on the panel. I am probably the least knowledgeable member of the Westwood team in that process, as I've only been here about a year and a half. I joined in the summer of 2023, but I've also been blessed to do 3 projects over the course of my career as a superintendent with the MSBA, and they've been incredible partners and continue to be incredible partners, as all of you in the room certainly know. I will say the team here from Vertex, from Doran Whittier, and I should also recognize our construction team at Bright Brothers. They have been, this building is a labor of love for the community. It is a wonderful space educationally. I look forward when we do the tours later to talk about what this space means for the education of children, what it means for the learning opportunities that are here. And I'll say one of the things that I always say, our job is to educate students for their futures, not for our past. And there's a great nexus in the program today between how we think about the future of energy in buildings and we build that sustainable future while also creating learning environments for students that allow them to capture really the excitement and the joy of what their future education and what their career paths are going to be. So again, I want to welcome you all here on behalf of the Westwood Public Schools. Thank you to all of our panelists. Again, thank you to the MSBA, and we're very happy to have you here today. And I think with that, I'm going to introduce Mary Piketty from the MSBA.
Thank you. Good morning, Mary Piketty, Executive Director at the MSBA. Thank you so much to the superintendent and his entire team. Special thanks to the gentleman who was standing out in the cold in the parking lot, guiding us all here. Wonderful signage, good job. Certainly welcome to this morning's panel. I think you'll find it very interesting, and I will serve as your program moderator today. You may know I've been with the MSBA since 2007 and served as Director of Capital Planning for the last 15 years prior to becoming Executive Director. As mentioned, in that time, one of the quickest shifts in building construction that I've witnessed has been the adoption of electric sustainable technology to power new schools. So in the Commonwealth today, there are 20 new MSBA-funded schools operating with all-electric technology, and 13 of those 20 have geothermal systems for heating and cooling. Another 37 schools are either in design or construction. A total of 57 schools. That's pretty great. This shift in the direction of sustainable systems began in about 2018, before the Inflation Reduction Act credits were offered. But certainly the rate of this shift has been spurred by the availability of the federal tax credit, as well as the MSBA's increase to 3 incentive points, which was approved in July 2023. We're very happy to see so many faces here today to learn. What a wonderful opportunity for all of us to learn from our pioneer school districts who are here already operating schools using geothermal technology. Our thanks to Westwood, Belmont, Watertown, Lexington, and Acton-Boxborough, each of whom will have great information to share with you today. I hope you find their lessons helpful and instructive for your decision-making process. Hopefully, as you entered, you scanned the QR code. If you didn't have a chance to do that, that is where you'll find the agenda and other materials for today. If you didn't get a chance to do it, both Barbara and Melanie, who are right here, very good, thank you, Barbara and Melanie, are available to help you with that. We have structured today's program into topical segments with panelists presenting during each topic, and we'll take your questions at the end of each segment. First up, we're going to see a short video presentation. The video is about one of MSBA's completed new schools operating with a geothermal system. Acton-Boxborough's new Boardwalk Campus School, formerly known as the Douglas and Gates Elementary School, opened in August of 2022. Calling up to the podium, please, Kim Cullinane from Eversource will introduce this video. Kim is the manager for new construction at Eversource, but this morning she will also be wearing her Mass Save hat, and later she will be talking about Mass Save incentives. So Kim, please.
Good morning, everybody. It's a pleasure to be here this morning to introduce this video. I'm going to show in a moment. So Eversource produced this video of using the Acton-Boxborough Regional School District's Boardwalk Campus as an example of what any school project, new school project, major renovation project, anything that you're planning to do in the room here, what you can achieve. What you're going to hear in the video is talk from Kate, who's sitting to my left here, talk from myself, others from the superintendent, and also my vice president, talking about our partnership, talking about the success of the project, but also our partnership. And just a couple points on that. The partnership included setting an energy budget from the very, very earliest stages of the project, and sticking to that budget just like you would stick to a dollar budget, a capital budget, all the way through design, construction, and operation. So the partnership involved setting that target, providing some funding for technical assistance, providing some funding for support for the technologies that were installed. And I'm pleased to work with Kate and the Acton-Boxborough project, and also on this project too, and the team that's here today, took advantage of some of those same services that we'll talk about more later too. So with that, I'll just turn on the video. working with the Acton-Boxborough Regional School District since 2018 on this particular project, with the idea that it would be a carbon-free school.
There was a great deal of discussion about the needs of children and about the need for energy efficiency and cost conservation.
And they brought us into this discussion early on. As a result, we were really able to influence everything from making sure you select the right project manager, the architects, build the requirements.
Eversource was able to put resources in front of us that we would not otherwise have been able to access. They provided a clear path about the incentives that we would receive.
We were able to really think deeply about ways to make a healthy building and make one that was going to have a positive environmental impact.
Bringing Eversource as a sponsor of MassSave to the table from the beginning lent credibility.
If we said that Eversource was supporting us in this, it made a big difference in people's ability to believe in our ability to do that.
And the community responded with a lot of enthusiasm, a lot of excitement.
We set a performance standard, an EUI, energy use intensity target, which is basically energy budget divided by square footage, very similar to a miles per gallon metric.
This school is about 1/3 what a typical school would be. So it's not a marginal improvement, it's really a quantum improvement.
I'm thrilled to say the building was built on time, on budget, and the energy model set a very low energy target, and the building is operating below that target.
This is a carbon-free building. We use all electric to run this building, and we're bringing no fossil fuels into the building for operation.
So what we have is a hyper-efficient, all-electric geothermal system inside of a terrific building envelope.
The shell is built to passive house standards, extremely tight. There is no combustion that happens inside the building.
We have 65 geothermal wells under the playground, 600 feet deep. In the winter, we send near freezing water underground and comes back to us at 55 degrees. Then we warm it up a little more using a high-efficiency heat pump and send it out to the building. And in the summer, we reverse that. We have marvelous indoor air quality here. So we've slightly separated the ventilation system from additional heating and cooling. And those are two separable systems. It's filtered, it's warmed, and it's delivered to the classrooms clean and comfortable.
The carbon dioxide levels are intentionally set at a very comfortable, productive, healthy level. These schools are exemplars of healthy productivity for students and staff.
Teachers and students can touch the thermostat and gives them a reading on CO2 level in the classroom. The ceilings are sloped, and that's where we can make the windows extra big, and that helps us bounce daylight into the classroom. It's also a net zero water building. The roof catches rainwater, and we store that in a 20,000 gallon tank outside, and that water is used to flush our toilet systems.
The setting was picked with the connection to the wetlands to put the environment front and center in their education and remind students of that.
We plan to put in solar plus a battery and have this building become a net zero building.
This is really a remarkable building that is exceeding all of the expectations we had.
This building is a fabulous example of what is possible.
To be able to replace two aging schools with one really state-of-the-art facility just has such a profound impact on how we move forward.
Over time, we're hoping to get every single new construction project to build to this level.
Lots of school districts are looking to put up a building just like this. We have had numerous school districts contact us for tours, information.
The benefits of doing this, whether it's from an environmental standpoint, from a financial standpoint, from a frankly educating the kids standpoint, it's a no-brainer.
Thank you, Kim, for sharing that video. Great way to get the program today started. So now we're going to continue with a short tutorial about geothermal technology. Joining us now is Joel Mooney from Belmont's Permanent Building Committee, who will also be sharing a PowerPoint presentation on how a geothermal system works. Joel? It's Joel behind you. Okay, thank you.
Thank you, Mary, and good morning. Happy Friday. My name is Joel Mooney. I'm a professional engineer and a licensed site professional, and have been a member of the town of Belmont's Permanent Building Committee since its founding in 1999. I've served on numerous building committees over the last 30 years and currently am a member of the town's high and middle school building committee. While I'm not volunteering for the town of Belmont building committees, I'm a senior principal at Haley and Aldrich. I have over 4 decades of building and infrastructure design and construction experience. The goal of my talk this morning is to provide a high-level overview of ground source heat exchange systems, also referred to as geothermal systems. My focus is on the well field energy side of the ground source system. There is also a significant amount of planning and design required for for the portion of the ground source heat exchange system inside the building's mechanical room. Next slide, please. To get us all on the same page, ground source heat exchange is not hot rocks energy, which occurs in regions with high subsurface temperatures at shallow depths, such as in the western US or in Iceland. It's not steam collected from the subsurface to drive turbines for power, and it's not very deep boreholes a mile or more into the Earth's crust. Next slide, please. What we are doing with ground source heat exchange is capitalizing on the available energy from existing shallow ground conditions. The northeastern US has very stable subsurface temperatures, typically in the range of 50 to 55 degrees Fahrenheit. We have shallow rock. Thermal exchange in rock is 4 times better than in soil. And most structures in the Northeast have both heating and cooling loads, which promotes well-field balance. Next slide. Conceptually, these systems utilize the ground as a battery. Using pumps, which recirculate typically a water glycol mix, heat exchangers and compressors, these systems draw heat from the ground in the winter and reject heat to the ground in the summer. You need to continuously monitor the temperature of the well field to ensure system performance. While technology 20 to 30 years ago circulated groundwater in open wells for energy exchange, all systems being installed today are closed-loop systems. Closed-loop systems are stable and do not have long-term environmental impacts. Closed-loop wells do not circulate groundwater. This is why they're often referred to as boreholes versus wells. Closed-loop boreholes are cased through the soil and have piping grouted into the bedrock. Again, the thermal transfer happens in the bedrock. Supply and return lines circulate a water glycol mix from the piping in the grouted borehole back to the mechanical room inside the building. The standard well, readily installed by contractors in the region, is composed of a single U-bend 500 feet deep. If you need more thermal capacity per well, increasing the well depth or adjusting piping within the well, if you will, going to a double U-bend versus a single, can increase the thermal exchange per well. Next slide. Now that you have the basic understanding of what a ground source heat exchange system is, how do you incorporate it into your project? First, is it feasible? So you'll want to evaluate site geology. Is contamination present or other issues in the subsurface? What's the depth of bedrock? Are there spatial constraints with utilities, trees, landscape, building footprints, basements, and property line setbacks? Is there a permitting risk relative to aquifer protection or water and spoils management? What's the size of the well field and the estimated cost? Does this work within your budget? Ground source may not be viable at every site. You will want to identify deal breakers early. If you've determined ground source is feasible and is a go, the next step is to do a test well program to provide a basis of design and determine the thermal properties of the bedrock, the thermal exchange per well, the layout and spacing of the well field. The test well program will also provide valuable information on well constructability related to rock quality, the best drilling methods, spoils management, water volume generated by well drilling, its treatment and management, and well production, which will have a direct impact on cost. Ground source needs to be planned, designed, and integrated into the project like any other system. You need to define the contribution of ground source to the building's heating and cooling, and as necessary, design other systems to provide the remainder of the building's heating and cooling needs and meet project energy goals. And the effort to plan the system cannot be emphasized enough. Coordination with the architect and the MEP engineer is critical to define goals and objectives in the system. What are the heating and cooling load, and what's the plan to maintain well-field balance? As most systems are cooling dominant, you'll typically need to reject heat to keep the well field balanced. And once you have a concept for your system, how does it fit on your site? Ground source design needs to consider and integrate into other site, civil, and landscape aspects of the project. You'll want to design to avoid conflicts with utilities, trees and landscape, and property lines. And your design should also allow for future access and maintenance of the well field with minimum disruption. What controls and operational actions are then required to support the ground source system? The system will evolve as you work through the design process. There's recently been some movement towards putting ground source boreholes below buildings. So as a geotechnical engineer, I'd like to provide a little bit of a public service announcement here. Putting wells under buildings adds many more complexities to planning, design, construction, and maintenance, and project cost. And it will drive your structural and MEP engineers crazy. While this can be done, please try to develop other concepts and only do this as a last resort. Thank you.
Thank you, Joel. Before we head out, Joel, does anyone have questions for Joel? A lot of information to explore.
Well, write them down, I'll be around. Go ahead.
This gentleman is all around the United States, is only in the Northeast.
Good question. Geothermal is used throughout the U.S., but again, think of it this way. You've got well field temperatures at 50 to 55 degrees, okay? You're cooling, for cooling, you're probably trying to put in 40-degree temperature air into your building, and then for heating, it's probably at 70. So you want to be in that middle so that you don't have a lot of energy to get your cooling done or to get your heating done. So again, I think if we go back, can we go back a couple of slides? In that map of the US, Melanie? Yeah, I mean, again, I think that is basically the northern half of the US is probably the sweet spot for using ground source. Again, the farther south you get, you're going to spend a lot more energy getting your cooling done. Yes?
Talk about costs per well.
Cost per well varies dramatically. What's that?
About 50,000.
Yeah, I mean, that's a rule of thumb. But again, it varies dramatically based on your site conditions and everything else.
And how about swing season temperature management? Is that easier or more difficult with ground source?
I guess what I would say is that, so again, you're talking about shoulder season heating and cooling. Again, I think what you want to do is you want to keep, and again, I think it was stated earlier, you want to keep that entering water temperature rather, again, fairly stable around 55 degrees. So you're going to want to continuously monitor that. So again, you're not reaching real deep to satisfy your cooling needs, and you're not reaching real deep to satisfy your heating needs. What you're going to have to do, again, most buildings are cooling dominant because they're being used 365 these days. What you're going to have to do is either add a cooling tower or figure out some other method to reject that heat out of that well field. And, we'll talk about that, what Belmont did a little bit later.
I think I saw another hand, Kat.
I had a question. You mentioned contaminants might be an issue in having successful boring. What type of contaminants? In the bedrock or?
I think the answer to that is C, all of the above. So what you want to do is you want to, just like every other aspect of site characterization, you will want to make sure that the environmental conditions, whether it's in the soil, whether it's in the rock, or whether it's in the water, that you're not going to make anything worse. And again, how does that relate to your spoils management? So again, you almost need to do a full environmental workup on your property, very similar to the other things that you work up to develop the design for the foundation or other site features.
So it's more that you don't want the well to cause additional contaminants versus some contaminant existing currently that would prohibit
Well,
using
again, you're
geothermal.
going to generate, each one of those wells you generate, you're gonna generate an awful lot of
Right.
water, and you're gonna generate spoils.
Exactly.
So I think you wanna understand what that is before you have to manage that for your project, because that will calculate into your, if you've got, say, chlorinated solvent contamination, which sinks in the subsurface because it's heavier than water, if you've got that in your rock, that's probably gonna kill your viability of your well field.
Thank you.
Great, so I
Yeah.
think, let's pause questions for now, get going panel, you gonna be with us for a little bit this
I
morning?
hope so.
Perfect, excellent. There'll be time for more questions, we'll move to our panel presentation. We're going to start off with our first presenter, Rob Fitzgerald. Rob is an architect from Dorr and Whittier who designed this beautiful school, Pine Hill Elementary. This segment will begin with information about siting and constructing a geothermal well. Rob?
Thank you, Mary. Good morning. The Pine Hill Elementary School is Dorr and Whittier's first geothermal system design. I learned that the installation of the geothermal system is a very different process than installing a conventional fossil fuel system. With a geothermal system, a lot of exploratory work, including testing and research, is required at the beginning of school design. Of the school design process in order to understand whether using a geothermal system is possible on your site and what the estimated cost will be. Let me explain. The architect, civil engineer, geotechnical engineer, geothermal engineer, and mechanical engineer work in close collaboration from the initial study phase. The layout of the building, particularly the mechanical room, is important relative to where on the site the wells could potentially be located. Ideally, the well field should be situated as close as possible to the mechanical room to minimize piping distance. Also, understanding the extent of possible bedrock on your site is important. Bedrock is helpful for thermal conductivity and typically makes for easier drilling than having to install a metal casing to keep a hole open in sand or other soils. However, shallow bedrock too near the surface can increase costs for trenching out for horizontal piping. Drilling a test well helps to provide some much needed geological information. This should ideally be the same depth and type planned for your future well field. This will also help to determine how easy or how hard it is to drill to the planned depth and how much water inflow there is. When the test well is done, it will need to be tested to determine thermal conductivity. In a perfect situation, this test well would be installed within the location of the future well field. At Pine Hill, however, site access was difficult, and we had to do it at a location that wasn't as conducive to incorporate into a permanent well field. A detailed hourly energy model needs to be prepared to determine heating and cooling loads on the well field. This is critical. The earlier that this can be completed in the design process, the earlier you will have a good handle on the number of wells you needed. On Pine Hill, our engineer initially used a conservative number to estimate how many wells would be necessary to heat and cool the school. The study phase included 80 wells, and the architectural team, working closely with our mechanical engineer, our sustainability consultant, and the peer review engineer from Eversource, we were able to focus on maximizing the exterior envelope first by super insulating the walls and the roof, transitions, targeting a very low infiltration rate, and a low window to wall ratio. On Pine Hill, that was about 21%. This enabled the HVAC system to be downsized and a reduction in wells from 80 to 60. For an expectation on construction duration at Pine Hill, it was roughly 5 months for the wells and roughly 6 months for the rest of the piping, bulk, and connections. Next up is Bill Lavallo.
Thank you. Good morning, everyone. My name is Bill Lavallo. I chair the Belmont Middle High School Building Committee since its inception in 2016. I'm also a member with Joel of the Permanent Building Committee of Belmont. Actually, my paying job, my second job is managing principal at LeMessurier with Structural Engineers, and I'm here to talk to you about Belmont's experience. I've been informed that Belmont School Building Project was one of the earlier school geothermal projects. So the scope of that project was to combine middle school with the original high school on that site. We ended up with a design enrollment of 2,215 students. So it was a big school, and as a result of that, the geothermal system was I'd say, very large. There were 283 wells for that project. By designing the high school with the middle school, the complex with the geothermal system and an all-electric chillers and pump system, this all-electric building had an increased electrical consumption by about a third from what our original site building had, which was a smaller building. Our solar system on the roof then reduces that increased demand by approximately a third on the annual demand of the electrical energy for the entire building. By way of background, the high school had two phases. The first phase was, the middle and high school had two phases. The first phase was the high school phase, which opened in 2021. And last year we opened our middle school phase, the second phase, and completed the project. Both of the phases were on time with the original project schedule. And the full geothermal system has been operating since we opened our second phase last year. The system now is well balanced and operating efficiently, but I can say we continue to monitor the building systems to make improvements to improve on that efficiency. And I'll explain a little bit more of that later in the presentation. But let me first tell you about Belmont's experience constructing the well field. As I mentioned earlier, we've got a very large well field. We built on the same site as the old building, and the site has a pond adjacent to it called Clay Pit Pond. There's a reason for that name. The entire site is filled with clay. So it required us to drill through about 85 feet of pure clay before we reached the bedrock. And as Joel said, that's where we transfer the heat through that bedrock. The ground became saturated with water during drilling, and the consistency of that site turned to about 5 times thicker than pancake batter. And so that was a problem, right? And things came to a halt during construction because of the potentially unfiltered runoff of this water, the spoiled water, into our adjacent clay pit pond, and because working conditions became so unsafe and just standing in all of the standing water and muck. The construction team built a dike around each well field to control it, but the water kept coming up into the dike. So we hired an expert, the town, on the town side, Tracy Ogden, who's been, has a reputation in the local industry, expert in geothermal wells, to advise the owner on installation matters that were being suggested by the construction group. And while the owner didn't direct the design and construction team, we brought on a level of expertise that allowed informed conversation, and we believe it assisted in the successful completion of the well field, which didn't delay the overall project. So here's some more information I'll give you about Belmont's experience during the construction of our well field. Like I said, there were 283 wells. They were divided into 3 separate well fields, and they are now under permanently landscaped areas in parking, not under our building. I'm the structural engineer who says don't put them under the building. Each well is 500 feet deep. It's a U-bend single closed loop well, and they're 20 feet on center. The building is 450,000 square feet in total area, with 100% of the heating and cooling sourced from those well fields. No other source of energy is provided. So Belmont's fortunate to have a permanent building committee with a large breadth of building design and construction experience, which allowed us to be a bit more proactive than maybe some districts might be in similar situations. So we spent a lot of time in extensive planning and discussing the managing of the drill water and spoils before even starting construction. Of course, as I said, I'm a Belmont resident. I know some of the residents that are on COMCOM. We had lots of conversation with COMCOM because they had influence control over our site. We researched when and how much to complete in the well field prior to installing the other site activities. For instance, what we heard on our neighboring in Cambridge, the King Open School, they had challenges with damage to the well field piping, possibly due to construction sequencing. So what we learned is there's a preference to install the major site work first before installing horizontal piping, so you're not bringing heavy equipment back over the site and potentially damaging your horizontal connections to the well field. So we ended up doing it in that sequence, and we had good success. We researched, because our well field was very large, we researched, and we were bidding back in 2019 We researched regional expertise and capacity and drilling experience when assembling the bid list to ensure that we had good subcontractor bidding capabilities to meet the project schedule. And since our construction manager was at Skanska and they had a breadth of the nationally located throughout the US, they were able to leverage their other offices and bring in bid lists beyond New England. And we actually ended up with a contracting group called Chesapeake Drilling, and they were out of Maryland. And again, like I said, we had some starts and stops that were challenging, but we did finish on time. So I'd have to say that now I'd say the industry has caught up, especially in New England, with some of these demands. I'm not sure the experience for your districts would be the same as ours, needing to reach beyond the New England border. As Joel said, water and soil management is a very big deal. Don't assume water can be managed on site. Have your disposal permits ready for construction, plan for the worst case scenario, and then double it. Note that well field construction includes more than drilling and installing closed loop wells. It includes the well head connections to supply and return loops, pressure testing, and then commissioning and well field balancing that occurs later on during construction when you have the building loads tied in. And someone asked me if there's a concern with noise and vibration from well field installation. This activity is invasive. It will add noise and vibration to the construction site. But it's not a significant adverse effect to construction considering all the other aspects of construction that go on in your site. And especially even if you're in a residential neighborhood, which the Belmont project was, that's in the middle of houses and so forth. So we had good success on that side. At this point, I'm going to turn it over to Kate. Continue to talk about her experience.
Thank you, Bill. Nice to be with you all this morning. Nice to be here. Our system at Acton-Boxborough's Boardwalk building was designed with 72 wells to heat and cool the building at 175,000 square feet. The building committee did look at another scenario, considering another scenario that would reduce the wells by 7 to a total of 65 wells, and offsetting that by adding in an electric boiler that would provide some supplementary backup heat for severe cold weather. The building committee did wind up selecting that scenario because it was a cheaper capital cost up front at the time. Today, I think were the building committee to reconsider that decision, they might choose to build out the full 72 wells. The full well field would have provided additional capacity for both extreme cold and also heat waves. And many of you will remember that when we opened schools in September 2023, we had a pretty dramatic heat wave. Some schools in Massachusetts were closed for that heat wave, and we did okay through that and had cooling throughout the building, which some of our school buildings did not have. But we had classrooms that got up to 76 degrees. That was per the design when we checked back with the team. And if we had installed the full set of 72 wells, we would have been able to provide better cooling and have more capacity to get us through the heat that lies ahead, it appears.
Good morning, my name is Allie. Please rise to the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Have a great day.
Thank you, and now I am passing the microphone to Sean Newell in Lexington.
Good morning, everyone. My name is Sean Newell. I'm the Assistant Director for the Town of Lexington Facilities Department. I've been dealing with geothermal buildings since 2006. I've been dealing with open and closed loop geothermal systems. The case that I'm talking about is the Lexington Hastings Elementary School has been in operation for 3 years. Like Belmont and Acton-Boxborough, operational refinement is still work in progress. When we get to the discussion on maintenance, I will share how we have dealt with building issues, but first let me share our experience with constructing the well fields. Site logistics were challenging as the well fields were being installed on recreational play fields, while the existing building was still in use as swing space. The following would be recommended for districts just starting out regarding planning of the wells, and as you've heard everybody say, planning is critical. Pre-designed test bores of locations that where the geothermal wells are presumed to be installed to determine how much load can be placed in this area of the well fields. So having an early understanding of what the actual building load will be and having the right technical person on your team during the feasibility study, like the design engineer, a green engineer, DOER has helped out with us, geotechnical people, geothermal people, so big teams to be designing your building. And ultimately, how many wellheads would be needed to run the building's heating and cooling wells? Hastings was originally designed for 100 wells to heat and cool 110,000 square foot net zero elementary school. But ultimately, the number was reduced to 80 wells. This saved the town over $1 million of well construction at a $50,000 cost per well. That's obviously the Lexington case. Well fields, the actual borehole might differ in your situation. The well fields at Hastings School has 10 circuits with 8 wells on that circuit, so approximately 30% of those wells are located under asphalt and hard tops. The remaining 70% of the wells are under dirt, under the play fields, landscape, and portions of the playground. My recommendation is don't install any hardscape and definitely do not install under buildings. The original system design had the well manifolds and valves buried underground in an underground vault. This vault is considered a confined space which requires significant training and certification to work in, especially for people that are operating the building. So my suggestion is don't bury your manifolds, don't bury your valves, try to bring it up into either the building or a building that you can walk into to service it. So in hindsight, we would have been better served in creating an above ground mechanical room or space to allow for more easy access and better serviceability. Additionally, the geothermal mains run from the field under the building slab to the opposite side of the building. If we were to redesign this, we should have put the mechanical space right next to the geothermal well field. So hopefully the lines that go under that building never fail. I'll now hand it over to Christy Murphy.
Thank you. Hi, everybody. I'm Christy Murphy with the Vertex Companies. I am the project director for the new and ambitious Watertown High School project. In partnership with the MSBA, I'm working with Chin and Silas that you'll hear from later. So like every district, and probably many of you, Watertown was faced with many priorities when designing their new 720 student high school. They also, like many districts, faced the historic cost escalation post-pandemic. These competing priorities included a commitment to the community that we would be net zero, that we would be LEED Platinum, that we would double the on-site parking in order to get teachers and staff off of the neighborhood streets, and to create a small multi-purpose field on the site for the first time in Watertown's history that would allow for outdoor PE classes instead of having to walk about 0.3 miles to Victory Field. So being an urban community, Watertown didn't have many options for a new high school site. The preferred solution that emerged after studying 17 options was to build a 76,000 square foot temporary modular high school on a baseball field that the school will occupy for 2 to 3 academic years, allowing us to take down their existing high school and rebuild on their 4.25 acre site, to give you a sense of the size. The new high school is just over 200,000 square feet. That does not include the space below for 130 parking spaces. It's basically built right up to 2 of the 4 property lines. I share all of this for context so you understand the challenges of trying to design geothermal wells for Watertown, and how ultimately what we settled on was a hybrid system that includes both ground source and air source heat pumps with VRF ductless fan coil units for heating and cooling, without any fossil fuels. So like many high schools, the building will be the hub of the community and is expected to have long hours, activity 7 days a week, 365 days a year, particularly in the community spaces, gym, auditorium, black box, and the admin areas. The design team determined that these community spaces are ideal for geothermal and ground source heat pumps. So thinking of the earth as your battery, as you've heard, the year-round use provides equal charging of the earth with heat from the summer occupancy being used later for heating during the winter months and vice versa. That same level of exchange would not occur with the classroom wing that isn't in use at that same level. So the geothermal well design that emerged for us for this system, for those community spaces, was 14 wells. They're about 900 feet deep, looped into 3 zones, and the remainder of the school then is air source heat pumps and fully electrified. Our wells are located in essentially one succinct hardscape landscape area adjacent to the common street side of the school, and to Rob and Sean's points, very close to the mechanical room, which made for an efficient and cost-effective piping layout. This allowed the design team to then accommodate those other priorities like that very important play field without having to consider any future access requirements. So this hybrid solution ultimately contributes to Watertown's net zero goal by reducing the EUI by about 3 points, and the construction cost of about $850,000 was voted to be included into the final budget for the project. And the last metric I thought was interesting that we'd share is that the community spaces represent about 25% of the total square footage of the building, and those 14 wells do calculate to contribute to that equivalent, 25% of the total heating load. So I'm passing it back to Rob.
Thanks, Christy. Once the wells have been installed and tested, they really should not need access for future maintenance. The vault does not need regular maintenance, however, it should be located in a place with easy access should that be necessary. Once the geothermal system is installed, tested, and operating, it's a very low maintenance way to go as there are no moving parts. The only moving parts in the system after the installation are the pumps in the mechanical room. The fluid, also known as the water and glycol in the geothermal well field, would be maintained the same as it is for the building mechanical system. Back to Sean.
Thanks, Rob. So as you know, we've talked about geothermal systems as an underground system. So you need to have a way to identify where the well field is and have individual well fields located, possibly by GPS mapping them. It's very important for folks who will be tasked with the maintaining of the system long after the construction team has waved goodbye and fled the project. Additionally, since the system is out of sight being buried underground, I recommend formulating a proactive plan as to how you're going to chase a leak if one develops, like what happened in Lexington. So stay tuned for that story. It's important to plan ahead in design and specifications to make sure you get all of the as-built documents you need after construction in order to properly maintain the building systems. So this includes well field and site drawings, near map, aerial, Google Earth overlays of the well field, so you know exactly how the well field was laid out on the site. Specifically, that as-built must include aerial photos with landmarks, and piping of wells and drawings overlaid on the drawing. Even drone footage if you have to go that fine as the site work is being done. Third-party well consultant is critical, and commissioning agent to look over the work and verify proper installation and documentation. Go to Kate.
Speaking of leaks, during the first fall when we occupied the building, the construction team was working to demolish the old elementary school, which was side by side with the new building. And they were near the end of the demolition process and going after a transite pipe that had been left towards the end because of contamination. And a digger was working to get it, and in that process managed to snag a geothermal loop and tore it open. And we lost a lot of geothermal fluid out of the system with that. the system had to be, a lot of material had to be screened, we had to come up with more glycol, the system had to be refilled, balanced, air bled out of it. This was all handled by the contractor, but it certainly is important to have a clear set of drawings of wellfield locations for planning any subsurface work that's going to be happening down the line. And now I'm passing back to Bill Lavallo.
Thank you, Kate. I think we all have well-field stories, leaks, and so forth. But I'm going to talk about energy. So well-field energy, it can be repurposed. Belmont knew during the design of the building, that it would be predominantly a cooling load building, like Joel had said, for most of the buildings around here, which means annually we need to reject more heat into the wellfield than we're pulling out of the wellfield. And to ensure long-term health for the wellfield, so that our battery, the battery that we kind of use as an analogy, has balance over the energy flow annually, we need to reject the heat outside of the wellfield, that excess heat. Traditionally, that would be performed with, say, cooling towers on the roof or the ground, or some form of air-cooled chillers on the roof, but that has significant upfront costs of equipment, piping, power, and long-term costs in maintenance, and in our case, these would be on the roof, and thus we lose roof surface that was designed to completely have PV on it, so loss of renewables. So how do we know that we would have heat to reject? Our design team modeled the annual anticipated energy use in both winter and summer seasons, so the heating and cooling loads. And in Belmont's case, the annual cooling loads are predicted to be about 10% higher than the heating loads. This means that we would be putting about 10% more energy into the ground than we were extracting. We just kept running through the well field all this energy, thus ratcheting the well field temperature, ground temperature up year after year, which eventually would reduce the operating efficiency of the well field, and in extreme cases could render the well field ineffective in meeting your building demand needs. So our prior facility director was doing research during design across the country on different installations, large installations, and came across an installation with a heat rejection slab. So simply put, an exterior radiant slab that circulates heated water to warm the slab, and then in cooler weather, it's just basically transferring heat out of the system to the air. And the benefit of that is that if you have the real estate to do this, it's an exterior concrete slab. It's very economical to build, low operational costs because there's just small pumps running the water, and little to no maintenance costs. And since this is an annual balancing effort for the well field, this system can be run at any time, not in the summer, but when it's cooler out, to reject that heat over the course of the year. But the real cool opportunity here is that you can put these slabs at the building entrances and operate them during the winter to serve as snow melting systems, which is what Belmont eventually did. I'm going to turn this over now to Jen.
My name is Chin Lin, and I'm with Vertex Companies, and I'm the senior project manager for this particular project, and I'm also currently working on the Watertown High School. And so the OPM on the project, one of the things that we have to do is just making sure that everything goes smoothly in terms of the process. And we have the benefit of the sort of, not from your project, but from another project of ours, where the groundwater during construction causing a lot of problem in terms of not having a plan well ahead of time. And so in the planning process for this particular project, that we actually, with Rob's, with the design team, that we actually had the work with the Conservation Commission. In the this project is has wetland just outside of the building, that towards that side is wetland, and as well as on the other side. And wanting to avoid any well water runoff towards a wetland, that we work with the Conservation Commission to actually roll into the order condition that the groundwater disposal procedure and standard. The reason for doing that was because that if you do that ahead of time, you don't have to, when you you actually encounter the problem, you don't have to come to an agreement with the conservation, because at that time, if you have water running down to a wetland already, that most of the time the Conservation Commission is really upset about that issue. And so trying to avoid that and trying to avoid so that you can do the negotiation when everybody is calm and collective, and then so that you have an agreement, and then it is in the construction document as part of the condition. And then, so if that happens, there's no arguing, and everyone knows exactly what to do. And the other thing that the team did a really nice job with this particular project is that the two well fields are basically more or less corresponding to the two parking lot outside. And we benefited hugely from that from the construction perspective, because they actually had a delay in, they were having trouble installing the wells. I did not quite fully get the full picture, but the advantage is that because there's nothing else goes on top of the well field besides the parking lot and minor drainage system, it doesn't impact the rest of the project. So that effectively we were able to say that, well, I just have to get the system up and running before the HVAC system is up. And that allowed for sort of even though we know that they were delayed, that did not impact the critical path in terms of schedule for completion. And then so that's some of the benefits that we have. And then the other thing that we also, in terms of the, one of the things that George, who is the on-site project manager for Vertex also, and we were paying a lot of attention to when they were putting back when they were backfilling, or number one, there was a lot of testing. Every step of the way, we have continuous monitoring from the geothermal well designer during construction for every step of the way. And then, but we also, one of the things that we make sure that they do is that the proper encasement of the approximately 18 inches of sand all the way around the piping. The whole idea there is that if you have the sand there, you reduce the chance of anything, a piece of rock hitting the pipe, sort of providing some level of protection. And on top of that, they lay down warning tapes, so that anybody who is comes back later, they will be able to have at least some level of warning ahead of time. And that, Mary.
Great, thank you so much. All right, so I'm going to invite Joel back up to sit with our panel in case there's additional questions for him as well. Before we get started with questions, a round of applause for our pioneers who are sharing wonderful, multiple reasons for not to put geothermal wells under buildings. That's my first note on that right now. So who has questions for our team? Sir?
So once these systems are in and we're taking it over as a building, what kind of yearly maintenance do we have to do on that? And is there some kind of, do we have a specific type of BMS that we have included in these systems?
Anyone want to feel that?
I can feel it. So I operate a 12-year-old public service administration building where I sit, the offices, and it's a 24 well system. I think they're 500 feet? And it's probably one of the easiest buildings that I manage. It's that one and one of my oldest buildings, which is one of my elementary schools, the Mitchell, because it's got very few mechanical parts and there's no technology in that one. But the building that we manage where we sit is absolutely easy. We don't really do anything. I think I've replaced one pump in 7 years since I've been there. There was a seal that was leaking. We just replaced the pump. But we have it on the BMS system. I see it all the time. So we monitor it, but it's a very easy building to maintain.
Yeah, one of the things that I've mentioned about BMS is make sure that you have your BMS architecture for the town or the school system embedded in your specifications. That way you usually end up getting what you might want, what you can actually manipulate, control, repair. So even though it's a brand new building, you're going to have an operational cost on, especially if it's an integrated building. BMS, energy monitoring, lighting controls, be ready for that. It's, everybody thinks, oh, it's a brand new building, it shouldn't cost me anything for 5 years. That is definitely not the case. Most of your architectural firms, when they're doing energy modeling, will also do operating costs. You should be part of that conversation. In Lexington, all of our buildings are integrated. I can pull my buildings up on my phone right now if there was an issue, so I don't know if that's what you look for. Somebody also asked a question about the swing months. As long as your geothermal well design is proper and you're creating chilled water and hot water inside the building through a heat pump, you've got a 4-pipe system, you should be able to control through the swing months. It's when you run into 2-pipe systems and having changeovers, that's where I see swing problems happen, but I haven't had that issue in any of my geothermal buildings or all my air source heat pump buildings.
And Sean, part of this question too was ease of maintenance for the mechanical equipment.
Oh, so that goes back to how well is your facilities department built up? So do you have HVAC techs? Do you have electrical techs? Do you have on-call contracts to be able to take care of this stuff in a timely manner? And I'll get into the planning later in the discussion, but plan now, put your on-call contracts out, have people under your thumb, so to speak, to get things done when they need to get done. And really look at how you're gonna build your team and the training that needs to go to that team. And I think I talked about training near the end of the discussion about how you incorporate that in specifications and take that training.
But in general, these buildings are fewer moving parts, easier to maintain.
So if I could just ask, when you ask a question, if you could just say where you're from and what your title is, so we have a good sense of folks.
Elliot Nato, Facilities Director with Leominster Public Schools.
Thank you, sir. Ma'am?
Thank you. Carla Nazaro, I'm the chair of the Killam School Building Committee in Reading. We are deciding on an HVAC system on Wednesday, and we have gotten some options from our MEP contractors to say that we could dig these wells at a slant underneath the building, which is making me really nervous to hear this panel too, because we have a really tight site. So we'll see what they come up with on Wednesday. But my concern has always been, besides operating costs, besides what breaks down after warranties and what that does to a district, and how that affects, I'm also on the school committee, so how does that affect our budget for what we give to our students if we're spending a lot of that money fixing issues? So that's part of my concern, which I hope we'll hear about later on. Noise drilling, noise during construction, because we are going to be on the same site with the existing school when we're building the new school. We have really poor window quality in our existing school, so I'm concerned about noise during the day when the students are there. But I think my biggest concern is and I've heard some ways that the actual wells can be compromised. If wells are compromised, what does that mean? I know they can be in individual loops. Can you shut off loops? You know, if you're gonna go digging for problems, you know, in my mind, I say, what happened?
I think you're jumping ahead to 4 panels, so
Yeah.
we'll stop you, because there's a lot of concerns there,
Yeah.
right? And so we did hear some concerns about noise and vibration being an issue with wells. Which question do you want addressed?
I want,
someone tell her she's gonna be okay.
Well compromised. I wanna know if I need to move out of town after.
Just go to the grocery store, that's all. No, seriously, I apologize.
Well
Well
compromised is probably
compromised is probably a good question.
And can they be turned off individually?
So everyone's looking at me. We heard about putting wells under the building, but how many on this panel had problems with well fields after they were installed?
But not compromised. I mean, I don't know.
Also, something to do with the well field that, you know, so think about this. If it's under your building and you're starting constructing the building and there's still a problem, you're impacting the building. And that, let alone what happens in the future. Not the best of ideas, but you have to make a decision for your community. None of us have well fields under the building for a very good reason.
So do individual wells, can you shut off individual wells then?
But only if they're tied to a it would be the whole circuit.
Usually they bundle together a number of wells into a circuit, and then typically you can shut down the circuit or isolate the circuit, but not frequently. It's not the individual wells because that's too difficult and too many.
Some grouping. Don, did you have something to add?
Part of my presentation, our discussion later on, is going to be on this very subject of
Excellent.
detecting and what to do.
Perfect. Sir?
Just a quick question for you guys, since you guys are talking about wells not under buildings. She asked slanted wells under the building. So are you referring to damage to well heads or to the piping that's going below the building?
For me, it's piping. So below the building is a no, I would never do that.
Just want to verify it.
I think if you ask somebody if there was an issue, and they're gonna say it's a 1 in a million chance, you can say bull. What am I supposed to do when I lose that cooling and heating load under a building? How are we gonna approach that? Because when the building is done, 1 year later, your warranty's done. It's on you.
But the head is outside the building.
So, yeah, so you've got the well head that you have to approach, but then if your piping is under the building, and the piping is leaking, how are you gonna get to it?
I guess
You're gonna have to shut.
I was referring to the bore.
Oh, the bore is outside of the building?
The bore starts outside the building.
Yep.
With a head.
Yep.
And slanted underneath the building.
Oh, slanted underneath the building.
That's what she's asked.
Let me speak to that a little bit. As far as wells, 500 feet deep, think of them as like a piece of spaghetti. You have better control on the well drilling in a vertical fashion. If you start drilling on an angled fashion, that drill string is going to wander all over the place. You have a lot higher percentage probability of wells running into each other or crossing, and also you have, if you can't hold that center to center spacing, right, you're not going to be able, your well field is going to be less efficient. So again, I think there's these compounding features that drive you to not do it under the building.
But her fear is being compromised after the well has been created, or the borehole's been created.
Well, again, never say never, right? I mean,
yes,
Murphy's Law
just want to make sure
we
have the detail of that.
So one thing that you do not know is that if the two wells are, number one is that nothing is straight.
I totally get that.
And then, so that if you have two wells that are not, they did not cross, but they come pretty damn close, then you effectively have you lost one of the two wells. And then you would not know that in the process.
So I think what we have represented here is 4 districts who have experience with wells. None of them looked at slanted wells. So that would really be incumbent upon who's ever proposing that, I think, to show you a situation where it has perhaps been used successfully, operating well, no issues. It's a little troubling to see the number of hands that just got raised on this panel in terms of how many people have had leaks. 1 in a million.
So I think what you would want to do is evaluate other options to get more thermal capacity per well. That could be by putting those wells longer and deeper, or again, putting more piping into that well so that the heat transfer per linear foot is improved over a normal U-bed.
And I also want to note, we've all handled these situations. It's all, these are sort of workaday problems that you can figure out. Sean described our situation got handled. It just, you want to be able to get at things if you need to, right? So
we won't be doing it. Thank you.
So earlier I saw a hand raised over here.
Can I just quickly answer one question about the noise? This project was built with the existing school in operation, and we have to deal with, we have blasting and drilling. one of the things that the contractor did, I really appreciate that, was that they took the topsoil, created a big mound in between the construction site and the existing building. They didn't even know that we were drilling. It was like a
Okay, one last question, time for one last question before break. Anybody? Yes, sir.
Patrick Roach, I'm the Chief Financial and Operations Officer at Springfield. How long did it take to balance your systems, like get them comfortable and running well?
We will talk about that
Okay.
later, yeah.
Okay, great. So, we're ready for a 10-minute break. And when we return, we're gonna be talking about skill sets for operation, tips for maintaining a geothermal system. And Bill, you're gonna kick us off for this session.
Okay, that was quick. Thank you, Mary. Who's overseeing your system? So during the later stages of our design, an outside consultant reached out to Belmont to ask about our plans for design and coordination. So design coordination with construction coordination with district operation. And as we were starting to try to stitch all that together, it became apparent for us that while we do have all those aspects covered in our scope, there wasn't one entity who was championing the owner's side and the owner's expectation from design to construction and through commissioning into continued operation. That's not to say that our design team wasn't doing what it's supposed to and everyone else, it just didn't have that single champion. So we realized the potential, I don't want to use shortcomings, it sounds strong, but we were a little short on what we had at the time and learned of the long-term benefits that we can expect with outsourcing oversight of this for the operational efficiency of the system. So out of this process was born an RFQ for specific design and oversight expertise that would lobby for the owner, so for Belmont's expectations, and ensure that the system design matches the owner's expectations and the system constructed will operate effectively to meet the owner's expectations. And our OPM-CHA saw that additional additional scope effort that we ended up having directly to the building committee as a hired consultant. In the end, we hired a firm called IDS, Interval Data Systems, who could likely be the single most influential consultant for us on this project when it comes to building comfort operations. They have been the owner's champion through design and construction and through commissioning and now, into the warranty and now pretty much, since we're close out with Skanska, into operations without the resources of the design and construction team. They reviewed the sequence of design operation. They participated in subcontractor control meetings. They monitored startup operations and tracked tens of thousands of data points daily to review trends and advise on systems that were not properly operated to the sequence of operations. Sometimes identifying those anomalies before the contractors or facilities would even see them in alarms in the BMS system. They love data. These people are just data freaks. I shouldn't use freaks, but they just love the stuff. So BMS learned that while Belmont learned that while the BMS, if programmed well, would help operate the building and help learn building trends and adjust as needed, it does not track trends or report energy uses in such detail that one could see where a unit is running 6 hours longer each day than planned. But the algorithms that IDS developed for this project does just that. And IDS provides that information to facilities, and facilities can go straight in and adjust the equipment to be running more effectively in the building. So during construction, IDS provided that information to the contractors as they were working on the building commissioning and helped that process move along more successfully to meet the strict energy performance targets that we had. We ask ourselves, can Belmont find skilled staff that can dig deep into these highly complex building functions? I hear at a municipal pay scale, it's hard to attract that talent. And if you have talent that trains up to these complex buildings, they often move on to private work opportunities where these skill sets may bring them better pay. So utilizing outside consultants can be less of a cost than a full-time consultant. They don't have to be in the building because their interface is all web-based. You can pull it up on your phone. And typically they have depth so that if someone leaves, they provide that continuity with another person in the firm. And you know, the best part is that you don't have to go through another hiring and training process when that person leaves. But certainly if you need to plan ahead. Budget for the internal talent and outside consultants that you'll need to effectively operate these highly complex buildings. And even if you have a good relationship with your mechanical engineer and on this project, that part of building operations is not something they typically specialize in. At least that's what I found. So at this point, I'm going to pass it back to Kate.
Can you all hear me okay? Yeah, I'm just going to go editorial for a minute and say I think this is one of the most, it's a question that's on top of mind for a lot of people is how do you need to hire more staff for these buildings, and that's what we're speaking about here. I think the answer is, yeah, will evolve over time and be different for different districts. I know, my understanding is that Winchester is creating a new sort of a stepped up position called building manager instead of head custodian. We've talked about that at Acton-Boxborough, have not done that. But you know, I think we'll see what happens over time. We'll all be we're on a learning curve with each other, right? So at Acton-Boxborough, the building has been open for 2+ years. It is running very smoothly. The energy use was projected at 23.1 BUI and is running below that. I had thought I was going to spend a lot of time on plug load, have not had to do that. Been really grateful to have the building perform so effectively. We do have a few issues to chase down related to building operation, however. When we opened the building, there was still a great deal that needed to be done, and the construction team was working behind us on evening shifts and weekends all through the first fall of operation. Just doing the balancing and all kinds of really significant tasks. As we near the end of the construction closeout, Eversource has a terrific incentive that is part of the Path 1 Net Zero program called Verification Incentive, and they will help supplement the cost of keeping a commissioning agent in place for the first year of operation, and we took advantage of that and actually brought in a different commissioning agent than had been involved during construction, and he has been marvelous, provided some of the same support that Bill was talking about. And we have kept him on for a second year with a smaller scope. He's provided really important help in identifying and resolving issues that were still open because these buildings are complex that you don't just turn the key in the lock and step into a building that's up and running. Among the issues that we've had to work with is that the 5 big heat pumps that are in the center of the mechanical room from water furnace, the logic sequence from them was not working correctly. We came back from winter break. We had stepped them down a little bit of setback for the winter break, and only one of the 10 chambers came on. The building wasn't warm enough. Just that kind of stuff persisting. And our HVAC guy had overridden some of the building settings in order to not have complaints coming in from the building, which is not the right solution. So we've been working through that. And in addition, 2 of the 7 rooftop units turned out didn't have any demand control ventilation installed, even though it had been spec'd. So he picked that up, and we're working on resolving that. Thank you. And on to Jim.
As I said, that as the OPM on the job, I take the task as that making sure that there's appropriate people at different stage of the project to support the team. Melanie, can we have that first slide up? Doesn't matter. I'll talk through it. So one of the things that we did for this particular project, once we know we want to achieve the ultra low EI, and then that we're participating in the Eversource's program and effectively promising the town that we are going to reach the below 25 UI goal with a verification process. I didn't want to be responsible for that, so I'm trying to find out somebody so that I can make sure that you don't have this at the end of the job of people pointing, because it's not the responsibility of the designer, it's not the responsibility of the contractor, and not the commissioning agent. And so we eventually arrived at the same point that Belmont did, was finding a automation consultant And the subtlety, the difference is that we asked the question early on, and then we actually brought ideas into the project in the design development phase. And that has a huge amount of benefit because I also don't want ideas to say that the building wasn't designed right, so we can't get there. And so that they were there from, not quite day one, but from design development, so that they know every step of the way, participated with the HVAC engineer and the well designer, and then actually we have them do the sequence of operations specification. And so we had the benefit of the design and somebody making sure that the design team and everything, having one extra pair of eyes in the job to be able to do that. And then they are actually still on the project, and we just, we hired them to, we also did something a little bit unusual. I made sure that I want to make sure that somebody's here to hand in to Eversource the 12 months verification process. So the contract was set up that they start up from DD, but they have to end with a 12-month operating cycle at 25 EUI or below. That was the condition. So that way, that I have some assurance that somebody is going to be responsible to help the school get to there. And we actually have just recently purchased 1 additional year of their service for the monitoring, and I'll go over that in a little bit more detail. But one other thing in terms of skill set is that to achieve the low EUI and the system, the building envelope need to be as good as you can get. So we also included additional envelope consultant and additional building commissioning scope in the both design and construction phase, so that we make sure that it's designed correctly and executed correctly, so we have some comfort level to know that the building was built properly. And then that process also go into the startup process, and then in terms of the geothermal well, we actually so we have the well designer, and then but we also have the scope of service to have them to monitor the entire installation sequence, so that somebody is watching over the contractor to make sure everything is done properly.
Every day.
Every day, it's 100%. So when the well, the well installation contractor is on site, they're on site, so they're there to watch every step of the way, because that to many people's point that we don't want to come back and fix a leak. That's just nightmarish. And so we just want to build in as many steps as possible, and as many verification in terms of testing and verification in the construction phase. Rob.
Thanks, Jim. Jim used up a lot of airtime here, so I'm just going to get to my. That was good. Like Bill, we found that it's important to work closely with the end user to fine-tune the energy use. Facilitated by a controls consultant that can understand the sub-metering data that is gathered by a sophisticated HVAC system. This allowed for clear communication back to the owner on strategies for reducing energy consumption and cost. This is really a critical component in keeping your predicted energy use intensity down. As Chin mentioned, it's important to have a building operator that has an understanding of or can be trained on how geothermal systems work, and that can interpret the data reports from the building management system. Pass this on to Silas.
Has opened 2 net zero gold grade schools that are completely cooled and heated by air source heat pumps. So a little bit different than what we've been talking about on geothermal, but same basic ideas within a building, good thermal barriers on the building, and all electric. So we worked on individual systems over time that were installed in these buildings, but we'd never really put them in a single building to see how that building would work. And it took us about a year to get the buildings up and running correctly. Both myself, the architect, the engineers, all had problems that we had with how the building was set up, and ultimately with the administration then its use of the building as well. Ultimately, we were able to figure it out, and both schools are running great at this point. But it does bring up a problem that you have to think about. These buildings are complicated. You all have, been in buildings before, and typical things that you guys see from a maintenance perspective might be something along the lines of a light goes out. Well, how does your maintenance staff take care of that? They go and they look at the light switch and they look at the light bulb. In a modern building, new building, a net zero building, there's gonna be all sorts of controls on it. There's gonna be Wi-Fi or land-based light switches. There's gonna be harvesting sensors on your ceiling. There's gonna be occupancy sensors on your ceiling. There's gonna be a control box that's controlling your lights. There may even be a BMS or a management control system in the background. It's not as simple as it was before. Your staff that you have, your technical staff that you have, that you maintain your buildings, they're gonna have to learn new things about how to maintain the building. It's not just the geothermal that's gonna be complicated. It's the whole building. There are so many control systems in a building nowadays, from PVs to HVAC to lighting to security to you get into it, MNS, and you can go on and on and on about them. So, as you've heard before, prepare, but it's not just prepare for the geothermal, it's prepare for all the control systems that you're going to start to see in your schools, your new buildings. Watertown took a little look ahead of time and decided that they actually needed to have somebody in who knew controls and to be able to manage these types of systems. Before the buildings were built or completely built, they put out for a position, and I ended up taking the position. So to give you an idea where I came from, I've been 30 years in software development with an understanding of building controls, and last 10 years I've been working in facilities in some ways or energy management. Those are the type of people you want to have when you're looking at a new building. It's not just the HVAC people. The HVAC people might be able to tell you an individual item or an individual piece of machinery. They're not going to be able to tell you the overall building, the BMS, the controls, the lighting, or any of those other items. Okay. So right now, I think you've heard, we're building a new high school. We're putting geothermal in it, and I want to know what that means. I've actually toured this school before to try to understand what issues are going to happen with geothermal. What things do I need to worry about? How am I going to integrate it within the building? What things are going to be the issues I'm going to be looking for? Like, is there a spike in heat temperature? Is the battery, is your geothermal working right? Is it changing temperatures in ways I'm not expected or outside the norm? Those are the types of things I'm going to be watching for and looking out for. All it comes down to, plan ahead. I know we've talked a little bit about getting new staff, but minimum, train your staff you have now. Not just on geothermal, but all the other items that are going to be in a new building. Thanks.
Great, Silas. I think that's really important. And I know the first session was almost sort of like ripping that Band-Aid off, right? Everybody got everyone a little nervous, but I think 17 years at the MSBA, certainly looking at schools turnover each year, what is the norm is 1 to 2 years of adjustments of learning how to use a new building. Doesn't matter what the fuel source is, that's what you're hearing from these folks. Be prepared. Expect to have to staff your building. Focus on the new qualifications that your folks need. provide professional development for your team. You know, I know our board members sitting behind me, you know, if you were ever at a facilities assessment, we focus on educational professional development, facilities professional development, critical. And supplement your existing staff with consultant contracts as needed, plan ahead. I think Silas, you have said that 3 times, so I think that's worth repeating again, right? And we've always said, please involve your facility staff from the beginning of the project, in design, at the table, by your side. These are the folks that are going to keep your building going after the ribbon cutting, so remember that. So we have a few minutes, we're running a couple minutes late, but 2 questions from the crowd.
So I know you mentioned around training for existing staff. I'd just like to hear from folks what training resources have been most helpful for your existing staff as you've gotten adjusted with these new systems.
And where are you from?
Oh, sorry, Needham.
Thank you.
Repeat the question.
Yeah, no, it's how do we train our staff, right?
Yeah, and what
type of
resources for
training?
existing staff have been most helpful?
So I'll start with how do we train our staff on a new building, is we make sure that training specifications are put into the contract. We don't take training on a building until it's 100% commissioned and all of the as-built documents have been turned in. We don't do these onesie, twosie trainings. I also tell my personnel, do not sign a training report or a training session if the system is not up and running. So if they walk into a lighting system training and the guy goes, oh, that's just a glitch, the training stops right there. My guys will actually walk out of the room and I will say, you need to retrain them because your system is broken. So always understand that. The teams that are trying to get the contractor to leave by paying them and getting them out the door, we usually use that training as the hold. You haven't trained us yet, so there's that. And then we bring in contractors if we need to. We'll actually have those contractors come back and do a training on the building after the warranty period is over. So be ready to pay those people to give you a little bit more than what you got out of the building construction project.
What about training outside of the project? You know, there are BMS certifications that folks can go to. Have you done any work there?
Yeah, so depending on the system that you're getting, Invensys, Honeywell, Johnson Controls, Mitsubishi, Train, those trainings are there. They usually like to train the contractors because the contractors are only in the business. But if you develop a good rapport with the contractors, they can usually get your guys into those types of trainings. And again, we do a lot of training on site. Look at your collective bargaining agreements, look at your job descriptions, make sure that they're updated so that you can push those people to get training. You know, some of these trainings are in wherever, Wisconsin, Pennsylvania, Florida, Georgia. So how are you gonna get a union guy to go to those trainings? So usually we try to keep it in-house.
Any other questions before we move? No?
You were, Elliot Nato, Leominster Public Schools. We don't have in-house people. We contract out for our plumbing, HVAC, and all that. So when you're talking about, you know, it could affect the electrical and everything, do we have to have one specific contract that can do everything, or can the 3 or 4 contractors that we contract with do their separate parts now?
That's a great question, because let's just take that you have an N-Light system in school X and a Johnson Lighting Controls in Y, and they need to be certified to work on those.
That's what we deal with.
You got 2 contracts going that you need to get out the street on. However, if you get involved with the specifications and try to unify the items that you're getting by being included in specifications and keeping them as tight as you possibly can, you usually will start ending up with the same system. The GCs that bid the jobs, the electricians that bid the jobs, they know what Lexington likes and they'll accept these kind of submittals. So it really starts steering them to what they're submitting on the project to get what you want.
But will those contractors, would they have to maybe sub out something if they don't know it? Would that contractor have to call somebody
Again,
in
if
Florida
you
to
put an
come?
on-call contract out, put the specifications out there, you need to be certified in N-Light, but you must be able to subcontract out for these lighting systems.
Okay.
Anybody needs bid specifications for on-call, if I have them, please reach out, I'll give you the Lexington bid. You just have to find and replace Lexington with the name of your town, and hopefully it'll work for you.
Thank you.
Thank you for that, Sean. That's very helpful, and I think that that's part of, you know, what was said earlier about working together and learning from each other and getting good resources. I have been in certain seminars, not particular to this topic, but in general about towns sharing resources as well, so sharing staff, sharing energy managers, things of that nature. So if you're a smaller town in Massachusetts, you may want to consider talking with your neighbors and seeing if there's opportunities to pool resources. So I think in the interest of time, I'm going to move to occupant behavior.